Great. So thanks, Sarah, for the kind introduction, and good morning or good afternoon. From my side, from Berlin, Germany. I'm very happy for being here with you. So let's start finding the most suitable PFAS sum parameter method. After the nice talks yesterday and the talk today by Professor Lee, you all probably know about the diverse entry routes of PFAS into the environment. These various entry routes complicate monitoring of PFAS. As a second complication, regulatory of some PFAS as PFOS and PFOA led to an enormous number of substitutes, resulting in over 4,700, or as Professor Lee said, as about 7,000 different known PFAS. Many of them end up in the surface water. To reduce contamination here, a detection method is needed to identify hotspots or contamination level events. This method should also include new PFAS to avoid the substitution. To identify regulatory limits, to define regulatory limits, the results of such a method should be robust and should have a low detection limit. And for sure, for routine monitoring, it should be easy to handle. We looked for the two most promising PFAS sum parameter methods, which meet all these characteristics, at least in theory, and compared them with each other. So, before we have a closer look into the results of this comparison, let's recap the concept of PFAS sum parameters briefly. Target analytical approaches for PFAS monitoring in surface waters are limited to up to 53 different substances, which is only a very small percentage of these 7,000 different PFAS. That's why we try to detect all organically bound fluorine as the OF, and therefore we use fluorine-specific detection methods. All published sum parameter approaches consist of two crucial steps. First, the OF must be separated from inorganic fluorine, and second, it must be converted into detectable species. The two most common separation techniques, therefore, are the AOF, where organically bound fluorine is adsorbed onto activated carbon, and the EOF, where organically bound fluorine is extracted via solid phase extraction, SPE. Spoiler, both the AOF and the EOF cannot represent the complete OF, but more about that in the results. Conversion of the OF is done either by a combustion unit as part of the combustion ion chromatography, short CIC, or in the graphite furnace of a molecular absorption spectrometer, GFMAS. During the CIC, the organically bound fluorine is converted into hydrogen fluoride, which is adsorbed in a trapping solution. This trapping solution is then transferred into a IC using a conductivity detector for quantification. During GFMAS, samples are atomized in a graphite furnace. The addition of molecule-forming agents like gallium result in a diatomic fluoride in the gas phase. This absorbs a very characteristic wavelengths and can be quantified using a high-resolution optical system. For the comparison, we took surface water samples from the River Spree here in Berlin on 10 different locations. There are no known polluted sites next to the sampling locations, and all water quality parameters were normal. All samples were taken on the same day last summer. Using this sample set, we determined both sum parameters AOF and EOF, with both instrumental setups, CSC and GFMAS, following this scheme. So triplicates of all water samples were filtrated, and a small aliquot was used to determine the total fluorine content, which is mainly made up by inorganic fluoride. For AOF and EOF determination, we adjusted the pH to 2. Enrichment and inorganic fluoride cutoff were reached by loading and washing of the samples either on activated carbon for the AOF or respectively on HLB cartridges for EOF. The second was eluted using methanol, resulting in an EOF containing extract. Both procedures were optimized in previous studies by Wagner et al., respectively by Metzger et al., and both take about the same amount of time for the sample preparation. The activated carbon and an aliquot of the extract were combusted and formed HF as trapped in a phosphate buffer solution. For AOF determination using the GFMAS, one set of these AOF containing trapping solutions was aliquoted and transferred into the GFMAS system, as well as into the IC system. Aliquots of the extracts from the EOF determination could be used directly in the GFMAS. For the results and discussion, let's start with the EOF. Shown on this slide are the determined EOF mean values with standard deviations referring to the methodic triplicates plotted against the sample locations. Both the GFMAS determined and the CIC determined EOF values are in the same order of magnitude and show a similar trend along the sampling locations, except for the last 3 samples. Overall, EOF values determined with GFMAS are higher than those determined using CIC. Before thinking of a possible explanation, let's go on with the AOF results. Plotted are again the determined concentrations against the sample locations. Please note that the data points refer only to one set of samples because we were only able to aliquot one set of these AOF trapping solutions. The dashed gray line would represent the triplicate mean values of the AOF CIC determination. Standard deviation for the GFMAS values refer to instrumental triplicates. So, if we compare the 2 values on each sampling location, again, a similar trend in the same order of magnitude is determined with both instrumental setups. This time with the CIC values higher than the GFMAS values. It is to mention that some of the method values were below the instrumental LOQ as highlighted in the figure. It seems that both detection methods are superior for one sum parameter each. The reason here, therefore, could lay in the different substance groups preferred by the different separation methods. As mentioned before, none of the known separation method is perfect, and both AOF and EOF only represent a portion of the OF. It might be that also the instrumental setups show this preference in the composition of the different PFAS. But for now, we can state that both instrumental setups show similar results for both parameters, but are the parameters comparable to each other? The left figure compared the AOF values determined using CIC and the EOF values conducted with the GFMAS. All samples were measured in the methodical triplicate, and both sum parameters end up in similar trends and values in the same order of magnitude. Please note again that AOF-CIC measurements, the determined concentration often was below the LOQ, as again highlighted. On the right-hand side, you can see the EOF values plotted against the AOF values of the corresponding locations. This scatter plot reveals that the EOF is systematically lower by a factor of 1/4. Answering the question, yes, we are able to compare those parameters, and both have advantages and disadvantages. And therefore, we move now to my conclusion. If we have a look at the instrumental setups, we can state that both are powerful devices for fluorine trace analysis, but the GFMAS analysis is faster and more precise. We have lower standard deviations. Also, it is more sensitive. So we have an LOQ which is 3 times lower. Comparing AOF and EOF, we can state that both parameters were able to reveal organically bound fluorine concentrations in the sub-ppb range. AOF seems to represent a higher portion of the OF. Therefore, it should be more sensitive. But EOF values scattered much less and showed negligible blank values. The activated carbon is known to show a high fluoride background, resulting in lower reproducibility. For a more accurate determination of the organically bound fluorine, further optimization is needed. And with this, I would like to end my presentation. Many thanks to all of you for your time, and also to those who funded our study, the German Science Association, to our cooperation partners here in BAM, and also the German Federal Institute for Hydrology, to my supervisor Björn Mehrmann, and to the rest of his group, namely to Fabian Simon and to Markus von der Au. And special thanks to the ECEC committee for the organization, and now I'm curious about your questions.
Thank you very much, Leonard. That was a wonderful presentation. We do have time for questions. Janice, do we have questions in the chat or in Whova?
What is the CIC trapping solution?
Yes, therefore I go back to the slide with the method. The CIC trapping solution is a phosphate buffer. So yeah, it's about 10 milliliters where you just gas the HF into it and it will be trapped in there.